Have you ever wondered why a kettle boils loudly but a puddle quietly disappears on a sunny day? Let's uncover the science behind boiling and evaporation. Both boiling and evaporation involve turning a liquid into a gas, but they are not the same. Imagine you're heating water in a kettle. As the temperature hits 100 degrees Celsius, the entire liquid gets excited and bubbles are formed throughout the water. That's boiling, a rapid process that happens at a specific temperature called the boiling point. It's like a big party where everyone gets involved. Now think about a puddle on a hot summer day. Even without reaching 100 degrees Celsius, the water slowly disappears. That's evaporation, a quieter process. Only the surface molecule with enough energy escape into the air. It's like a sneak out. Only a few molecules leave at a time. In short, boiling is fast, loud, and involves the whole liquid at a specific temperature. Evaporation is slow, silent, and only happens at the surface, even at lower temperatures. So, the next time you see steam rising from your tea or a puddle shrinking under the sun, remember, they are both liquid turning into gas, but through different paths. Science is everywhere. Do not forget to like, share, and subscribe. Hello students, welcome to our second class on thermal physics. Students, if you remember, we have introduced the concept of thermal physics in the last class, where we have primarily talked about first the states of matter, that is solid, liquids and gases, and secondly we talked about how gases behave, and we talked about like the three main parameters of gases, that is pressure, volume and temperature. How do they affect each other? Boyle's law, Charles' law, Gay-Lussac's law, all those things we discussed. We also talked about the interconversion between states, that how solids converts to liquids, liquids converts to gases and vice versa. So all that was introduced in the last class. Today what are we doing? Today we are obviously taking this chapter further. But why am I telling you all this? Because this video will only make sense to you if you have already seen or watched the previous video. So if that is not the case, then I would strongly recommend you go back to that video and then you can start watching this particular video. Right, soon. So without wasting any time, let's start. Today we are first going to take one more aspect of thermal physics, that is thermal expansion. And as the name implies, this is expansion related with thermal energy. Now imagine, students, let's take an example of solids. Let's say this pen. This is composed of particles which are rigidly bound and they can only vibrate about their mean position. So when you supply thermal energy, those vibrations become more vigorous. They start vibrating with more extent. Obviously, what will that do? This will cause the thing to expand. But sometimes it might not be observable, but it is happening even if you're not observing it. You know, it is not like compulsory that you should be observing something. It is not the case here that expansion is happening, but it's at microscopic level, and that is why you cannot observe that. So, and vice versa also, that if you are imagining something to cool down, that is thermal energy is taken out of that, then in that case those vibration becomes less vigorous, and then you see what you see is thermal contraction. So thermal expansion, thermal contraction, I hope you are now able to understand that. Now let's talk about one more thing while we are talking about thermal expansion. Let's imagine a rod, let's say. All right, so let's take up a rod somewhat like this. Okay, now imagine this, students. Let's say this is a rod of length L. Okay, and what we are doing is we are putting a burner and we are providing thermal energy. Due to that, its temperature changes by delta T. So first thing that you all should understand, that let's say the change in length. What is this, students? Change in length. Okay, so this change in length is first of all going to be proportional to the change in temperature. Why so? More energy you supply, more expansion you would expect. There's no doubt about it, right, students? Secondly, of course, delta L should be proportional to L. Why? If you have more length, that means you have more particles. More particles, that means more scope of expansion. So anything that has a very large length, then you expect the expansion to be more as well. imagine, for example, railway tracks. So there railway tracks can be of hundreds of kilometers. Imagine if you have a railway track in one go, and from winters to summers the temperature rises, that expansion will be way too much, and it can also cause the buckling of, it can also cause the buckling of the railway tracks, which can be dangerous. The railway tracks might buckle, they might curve, and obviously that can pose a threat of the trains derailing from the tracks. So what do? We make the tracks in sections. So it is not like one continuous track, it is like multiple sections and always some gap being left in between them, right? So now can you relate with thermal expansion? In solids it might be less, in liquids it can be even more, in gases it can be even further more, right? But it does happen, students, right? So now you understand one more aspect of thermal physics, that is thermal expansion, right? But keep these two things in mind. This expansion will be more if the temperature changes more, and it will be more if the length is also more, right? And thirdly, obviously it depends on the material also. Some material would be easily expanding, some might not be that easily expanding, depending on how rigid the particles are, right students? How rigid the particles are that are basically composing the whole substance. Okay, so that is about thermal expansion. I've given you an example. There can be contraction also. For example, cables. So imagine there are cables between two poles, some electrical cables like this. What do you expect to happen now? So let's say you install a cable, you are not aware of the thermal expansion concept, and you install a cable like this during summers, okay, and it's already taut, it's already of fixed length, right between the two poles. Now imagine what is going to happen when winter is going to come. So when winter is going to come, this will try to contract, and when this will try to contract, it might apply a force on the poles, and there might be a situation where the cables might crack or break. That is why, what is more advisable, what is the right thing to do in summers? If you are installing the cable, that you let them loose a little. Why? So that even if they contract, there is a scope that the wire does not break. Okay, so that's about thermal expansion. Of course, we make use of thermal expansion in some way or the other. We will talk about that. That is a thermostat. But right now, I don't want to mix it up. So far so good. I think you should be able to understand what thermal expansion is. Thermal expansion is basically the expansion of an object or a substance that is caused by providing thermal energy to that substance, right students? So it can be a change in length, it can be a change in volume as well. So imagine a thermometer, like a clinical thermometer which works on the mercury thread. It also relies on thermal expansion. So when it is cold, the volume is less, and when it is hotter, the volume expands, and this expansion of mercury, that is the increase in volume of mercury, will do what? It will start rising, and therefore we can calibrate it. So let's say if this is at 0 degree, we pose a mark 0 degree here when it is melting ice, and when it is boiling water, we pose a 100 degree mark. So that is how you can actually calibrate a thermometer. So it also works on the concept of thermal expansion. So I hope now whatever you are seeing on the screen is clear to you, but we will talk about this now, that is a thermostat. Alright students, I give you a minute, you write down the definition. What is thermal expansion? It is basically the expansion of a substance on providing thermal energy or increasing thermal energy of that object. Alright students, so now let's talk about the basics again. I have written that for you. So generally all types of matter expand by heating and contract by cooling, right? Molecules of solids, for example, are in constant vibration, so they need a space to vibrate in freely. When solids are heated, molecule vibrates stronger with greater amplitude, right? Amplitude means the extent. The spaces needed for vibration of each molecule will increase. Expansion must take place to allow molecules to vibrate freely at higher temperature. So all that I have talked about, just I have written that for you. Alright, Now let's talk about a bimetallic strip, that is also a thermostat. Now what is a thermostat, students? Something that can control temperature. Imagine an electric iron. You have a calibration in that where you can always, adjust the temperature at which the iron will go for auto cut. So auto cut means its circuit will break and automatically it will be turned off, right? So we can always adjust that. How? Let's understand that. So if you are looking at this diagram again that I have for you, so it is a bimetallic strip. Now you understand why it is called a bimetallic strip, because it has one metal or alloy on one side and another metal or alloy on the other side, both having different scope of expansion. So as I was telling you, not every metal will show same extent of expansion. Some might easily respond to the change in temperature, some might not respond that easily, right? So let's say this is brass and this is steel, and let's imagine that brass expands more than steel, okay? So that is what is going to happen. When you are going to elevate the temperature, the steel will not expand that much, but brass wants to expand more. But the catch here is that they are both fused together, they are stuck to each other. So when they are stuck to each other and the temperature rises, they cannot let off each other. So what happens is they want to adjust that. They want the steel to expand less and brass to expand more. So this is the shape they will acquire. So now in this shape you can imagine both are still stuck together, but the length of steel is not that as much as is of the brass, right students? So this causes curving of the bimetallic strip. What does it cause? Curving, okay? Now let's come back to this. A bimetallic thermostat strip in the electric iron curves and breaks contact when the temperature reaches a certain value. So the circuit opens or cuts off, right? Okay, when the temperature of electric iron increases above a certain value, brass expands more than iron. So the bimetallic strip bends and contact opens, turning the heater off. So temperature stops rising, right? Alright, when the temperature of electric iron decreases, the strip straightens back, switching on the circuit again. Now you might be wondering what is all this. So give me a moment here, but if you want to take down anything that is important to you, please do that and then we move forward. Right students, so this is what it is. So this is an electric iron. What is going on inside? That is what I am trying to show here. So now imagine this is normal temperature, the contact is here, it is maintained with the circuit and the temperature starts rising. Now as the temperature starts rising, this expansion happens and it bends like this, right? So iron has to bend less and brass has to bend more, as in it has to expand more. So brass has to expand more and iron has to expand less. That is why it curves like this, and as soon as it curves like this contact breaks. Circuit stops operating, the heating coil stops operating, and then it starts contracting again and it gets back to this. When it gets back to this, then again the circuit is completed, again the iron starts functioning, then it reaches a particular temperature, then what you do is again the contact breaks. So somehow you are using these bimetallic strips to control the temperature of a substance. That is what a thermostat will do. Okay students, if you want to make a line diagram, you can do that. Otherwise we will always be sharing these slides with you and you can always come back to these slides whenever you want for revision. All right students, so yeah, so that was all qualitative discussion majorly that we did. Maybe in higher classes we will also do the quantitative analysis of all these things, but you should know that expansion happens more for gases, a little less for liquids and least for solids. Why so? Because you do know that in solids the particles are much more bound as compared to liquids, and liquids are more bound as compared to gases. Now let's revise again students. What is internal energy? The internal energy of a substance is the total energy of all its particles. I have told you, imagine the air in your room. In the last class we were discussing that all the particles have kinetic energy, right? What is the average measure of that? Temperature. More temperature means more average kinetic energy of each particle. Secondly, they also have a little of potential energy. So when we say internal energy, we will always mean the sum of kinetic and potential energies of all the particles that are inside the system. Okay, so the internal energy of a system is the total energy of all its particles, which includes kinetic energy. All right, students, kinetic energy plus potential energy. Keep that in mind, students. Kinetic energy plus potential energy. The higher the temperature of a substance, the greater the internal energy of the substance. We have talked about it because the particles are more vigorously moving. What changes can occur when heat exchange takes place? This is the most important thing, students, that if there is an exchange of thermal energy, if there is any exchange of thermal energy, it can either change the temperature or it can change the state. Okay, it can change the temperature or it can change the state. Imagine water at 0 degree, you are heating it, it's continuously the thermometer reading is rising, and that is what is happening. Thermometer reading is rising. Maybe it will reach 100 degrees Celsius, where it will reach its boiling point and it will start converting into the vapor state or in the gaseous state. Okay, so we will talk about that. Okay, we will talk about that, but before that we should talk about another term called specific heat capacity, because that is the main entity that will decide how the temperature is changing. I will repeat that again for you. This will decide how difficult it is for the temperature to change. I'll give you an example. Let's say you have 1 kilogram of water. Okay, students, you have 1 kilogram of water and then you have 1 kilogram of some other oil. Okay, but both are 1 kg. Okay, and now you are heating both of them. Do you think that oil and water will heat up equally? So you would normally imagine that oil gets heated up very easily, but water, it is a task to heat water. What does that tell you? Not everyone will have the same response, and it is always the case. Right now you are watching my video, some students might be catching things very easily, some would be a little on the slower side, they will take more time, maybe they would watch the video again. So that is about response. So we are providing the same effect, we are providing the same heat, but maybe the response won't be the same, right? So water, it might not heat up that easily, oil will heat up easily. You can also call it in a way inertia to the change in temperature, that how difficult it is for that substance to change the temperature. What do we call this? Specific heat capacity. We define it as the specific heat capacity as the amount of thermal energy required to raise the temperature of a unit mass of substance by 1 degree Celsius or 1 Kelvin. So imagine for water, for example, for water, approximately the specific heat capacity is 4200 joule. Look at the unit, students, per kg and then per Kelvin or per degree Celsius. Okay, so you need 4200 joule for 1 kg of water for the temperature to raise by 1 degree. That is how you define specific heat. So someone might have it, for example, 2000, then that substance is easily heating up because it only needs 2000 for that substance, 1 kg of that substance, to increase the temperature by 1 degree. Right, students? So yeah, so let's talk about that now. So if we say that, you want to heat up something, so can we say you need more heat if you have more mass? Imagine now, let's change this to 3 kg water. Let's change this to 3 kg water. Now, would you need same amount of heat for the temperature to rise? No. So this is 3 kilogram water. It will need more heat. So more heat is needed if you have more mass. More heat is needed if you want to change the temperature by greater extent. Okay. And therefore, the constant of proportionality, that is what we call as specific heat capacity. So delta Q, that is the heat exchange, is equal to MC delta T, or you may write this as C is equals to delta Q over M into delta T. That is why we define specific heat capacity as the amount of heat for unit mass for unit degree rise. So if you want to raise the temperature by 5 degree, you need to give 4200 times 5. If you need to change the temperature by 10 degree, then you need 10 times of this, right? If it is 1 kg water, for every degree you need this. If it is 3 kg water, you need 3 times. Isn't that easy, students? So specific heat capacity more means more difficult it is for the temperature to change. Keep that key point in mind. More specific heat capacity always would mean more heat needed. More heat needed. So can we say difficult for the temperature to change? Difficult for the temperature to change. Please make a note of this. More specific heat capacity. So for example, for ice, it is almost half. It's 2100. So ice gets heated up much easier as compared to water. You have felt that. Sometimes you might have felt it that, let's say there is a swimming pool, the tiles, the floor around the swimming pool is quite hot, it gets heated up easily, but when you jump into the water, you realize that it is not heated up that much. Why so, students? Because water has quite a good high specific heat capacity. Right, students? One more term I want to define here. Just keep it in mind that product of mass and specific heat capacity is called the total heat capacity. Okay, it's called so this is specific heat capacity and this is the total heat capacity. So imagine if it is 4200 for every degree rise, what will it be for 3 kg? 3 times of 4200. So that is going to be 12,600. So the total heat capacity of this is 4200, then this it will be 12,600 for every degree rise. So that is called the total heat capacity, just for the information. But right now all this, so this is related with the extended syllabus, not for the core syllabus, but again reminding you that there is no harm in knowing things because it will ultimately help you for your own confidence. Alright, so let's move forward then very quickly. You take down the information and then we will discuss the state change now. Okay? Alright. Okay, students. So let's do an example. An electric heating coil supplies 50 watt of power to a metal block of mass 0.5 kg. In 90 seconds, the temperature of the block is raised from 20 to 45. Calculate the specific heat capacity of the metal. State the assumptions you have made to arrive to this answer. Right. Students, so imagine you are providing heat to a metal. You are heating something. You have a heater coil. First, it is not necessary that the entire heat will go to the metal. Some of it might also go into the atmosphere in the surroundings. So if that is the case, you cannot say whatever heater is giving, it is entirely going to the metal. It's not 100% transfer to the metal. But if you are imagining that, then you can use that energy supplied by a heater is equal to the energy taken by the metal block. But that is not the practical situation. That is an ideal situation. So what is the assumption that we are taking? That entire heat of the coil is going into the metal block and there is no one else sharing that heat. Alright, students, so let's first calculate the energy, the electrical energy supplied by the heater coil. I hope you understand that is going to be power times time. We have discussed that in our previous unit, students. So this is going to be 50 and it is being operated for 90 seconds. So it is going to be 4,500, isn't it? Joules. So this is the thermal energy that entirely is going into the metal block. So let's write this as mc delta T that we have just. Okay, now let's talk about delta T. Students, delta T, whether it be in Kelvin or whether it be in degree Celsius, is the same thing. So imagine 20 degree and then it is 45 degree. How do you convert that into Kelvin? Do you remember? You add 273. So if you add 273, this will become 293 and then 303, 313 and then it is going to be 318. So the temperature might be different in different unit, but the change in temperature is still going to be 25 and it is still going to be 25. So that is a good thing about Kelvin and degree Celsius, that delta T does not depend on the choice of unit. The value depends on the choice of unit but not delta T. Alright, so delta Q is 4,500 M is given as 0.5, specific heat capacity is what we have to evaluate, and delta T is like 25. So let's do this calculation, students, very quickly, and we will take care about the unit as well. So it's going to be 4500 divided by 0.5 and then divided by 25. So I'm getting 360. All right, I'm getting 360. So the specific heat capacity is 360. What about the unit, students? Joule per kg per Kelvin or joule per kg per degree Celsius. There is no problem whatsoever. Both the units are equally good because delta T does not depend on the choice of unit in degree Celsius and Kelvin. It might be different for Fahrenheit, but we are not discussing Fahrenheit today. All right. Copy this down, then we move forward. One more thing, students, one more thing. Every time we solve a numerical, it's always recommended that you first try the numerical and then you go for the solution. Okay. So, change of state, heat exchange with the substance can also lead into a change of state. We of course know that while the temperature is not changing. This is very important. So, whenever state changes from solid to liquid, we call it as the melting point, and whenever it changes from liquid to gas state, then we call it as the boiling point. So, that point is fixed, as in at that transition the temperature does not change. So, you might be wondering where is the energy going then? So, imagine these are two particles. You are providing energy, you imagine them to vibrate more vigorously. Now, after a point what happens is that the bonds start getting weaker. So, when this energy goes into the bonds becoming a little weaker, that is where you see the state change. So, imagine in solids the force of attraction was stronger, in liquids it was a little weaker, and gases it was way weaker or almost no interaction. So, when you talk about state change, the energy is going to rise or raise the potential energy. It is raising the potential energy. It is not raising the kinetic energy. That is why when state change happens, energy goes into raising the potential energy, students, goes into raising the potential energy, and it's not raising the kinetic energy. So, at this particular moment you feel as if the thermometer is not showing any response. Even the heat is going, still the state change is not happening. So, for example, when ice is converting into water, at that point in time, that is the melting point, you won't see the thermometer reading changing from 0 degree. So, it is in a way the heat is hiding somewhere. That is why it's given the name latent heat. Okay, so latent word means hidden. So, heat is hiding somewhere, it's like that. Where L is called the specific latent heat, which can further be of two types, fusion and vaporization. So, fusion is this, of course this is fusion, and this is going to be vaporization. Students, we have discussed that this is also a phenomena where gas can convert into solid, that is deposition, or solid can convert to gas, that is sublimation, bypassing this particular liquid state. Alright students, so now you can imagine that delta Q is equals to ml. So, latent heat will have the unit of joule per kg. So, for example, latent heat of fusion of water, that is ice converting to water, is let us say 336000 joule per kg. Okay, 336000 joule per kg approximately. That means it takes 336000 joule for every kg of ice to get converted into water. So, that is way too much. So, state change always requires a lot more effort. Alright, so I have talked a lot. You can copy down the important stuff, then we move forward. Right students. So, okay. So, now let us talk about this boiling and evaporation. So many times in your previous classes also you have discussed that, but let us do this formality one more time. I do not want to skip this part. So, what is boiling? So, boiling occurs at the boiling point. Now, what is boiling point, students? Imagine you are heating something. Listen to everything that I talk very clearly. What happens is the vapor pressure of the liquid rises. The vapor pressure of the liquid rises. At one point, this pressure becomes equal to the atmospheric pressure outside. And then suddenly the particles start escaping. The vapor start escaping, and that is what you call as boiling. So for boiling to occur, boiling in fact is also affected by the outside pressure. So imagine you are in some humid region, the outside pressure can be more, and you can be at a higher altitude, their pressure can be less. So the boiling will occur at different temperatures. You might always have heard 100 degrees Celsius is the boiling point of water. That's true, but that is only specifically at 1 atmospheric pressure, that is 10 raised to the power 5 Pascal. But if there is a change, for example, water won't boil at 100 degree on the moon, because moon does not have any pressure. But I don't want to confuse you much here, but boiling is a situation where the pressure of the vapor inside the liquid becomes equal to the outside pressure. So it occurs whenever it occurs, that is called the boiling point. In normal circumstances, we take it as 100 degrees Celsius. Okay, occurs throughout the liquid, that is why we always call it as the bulk phenomena. Occurs rapidly. So when boiling starts, it is very quick transition of water to vapor state, and this entire water will escape in almost no time. Lastly, bubbles of gas appear inside the liquid, and this is a very common question, that what are these bubbles made of? They are obviously water vapor. So you can see these bubbles here. So these bubbles are basically water vapor, right? Or steam, you can say. Okay. So these bubbles starts forming, and that is how boiling is verified. Okay. Now what about evaporation? Evaporation is a completely different phenomena. It happens at all temperatures, even below boiling point. What happens here is that the surface particles which are more energetic, they will in a way convert to vapor state and escape. And that is what evaporation is. That is why evaporation is affected by the surface area. Isn't it, students? More surface area means more particles on the surface, more opportunity for the particles to go off the liquid, and that is why it is proportional to the surface area. It obviously is dependent on the temperature of the liquid. Agreed that it does not need a specific temperature for evaporation. But students, imagine there is 20-degree water, 40-degree water and 60-degree water. So 60-degree water will have more evaporation rate. Why? Because the particles are more energetic. Okay, so evaporation does depend on the temperature of the liquid. Keep that in mind. More temperature means more evaporation. Of course, a wind or an air current. Imagine, can you like there is a wind blowing here. So when there is a wind blowing here, the particles will escape along with the wind, and you would expect the rate of evaporation to increase. All right. So occurs at temperatures below boiling point, occurs only at the surface of the liquid. So not the entire particles are participating, occurs slowly and no bubbles are formed. And the last thing is the cooling effect of evaporation. Now what is this cooling effect, students? What happens here? So when the particles escape, what happens is the energetic particles escape. The energetic particles escape. Now listen to this, students. What are we left with? Low energy particles. What are we left with? Low energy particles. So low energy particles, so the average temperature falls, right? The average energy of the particle falls. So whenever evaporation occurs, the remaining liquid always will have lesser temperature. It will cause a cooling effect. Imagine you've just taken a bath, and let's say water particles are still on your body, on your face. What does that do? So when those water particles evaporate, you in a way feel a cooling effect, isn't it? So that is the cooling effect of evaporation, because then you are left with low energy particles. Okay, so evaporation always causes a cooling effect. I hope you have learned that in your previous classes, but just for the sake of telling you. So all this is about boiling. So boiling is conversion of liquid to vapor state at boiling point, and this is conversion of liquid to vapor state at a temperature below the boiling point. All right, copy down the important stuff, then we move forward. Okay students, so now let's talk about this very quickly. Solid, let's say this is in degrees Celsius, okay, and normal circumstances. So this temperature can be anything, let's say -25, and obviously let's say this is H2O, that is in ice form. Temperature rises 0 degree, this is the melting point students. State changes to liquid. So when you are supplying heat, so what is happening is continuously the heat is being absorbed by ice, but it is utilizing that to convert into the liquid state. Then again this liquid state, when entirely ice has converted to water, the temperature again starts rising. Then what happens is liquid starts converting into the vapor state or the gas state. This is what we call as vaporization, okay, and this is happening at a particular temperature, that is the boiling point. In normal circumstances it would be 100 degrees Celsius, okay. So during a state change there is no temperature change, keep that in mind. Then again the temperature starts rising, solid, liquid, gas. If vice versa happens, then we call it as freezing or fusion, and this one is called condensation. So you can also do vice versa. Now you have steam and you can take out heat and you can convert that back to water. So let's talk about that. So these changes, so this is giving you an idea of the latent heat of fusion. This is giving you the idea of latent heat of vaporization. What about the gradient of these students? So imagine if you have temperature on the y-axis or heat or time on the x-axis, and we are heating two different substances. Let's say substance A, the graph is, let me take a color, okay. For substance A the graph is like this, and for substance B the graph is like this, okay. Now tell me which one do you expect to have more specific heat capacity. Let's say they both were 1 kg, A and B, both were 1 kg. What do you see? In A the temperature is rising easily, in B the temperature is not rising that easily. That means specific heat capacity of B is greater than the specific heat capacity of A. This is very important students. Where do you see the temperature rising quickly? A. That means A has lesser specific heat capacity. Alright, so this is the heating curve. We can talk about the cooling curve also now. Alright, so cooling curve is vice versa, gas converting to liquid, that is called condensation, and then this is called freezing or fusion. A cooling curve is like a heating curve but is the mirror image of it. Of course you do understand that, so not wasting time on this, let's move forward. Okay, let's start with this question. Pause the video, try this, and then we move forward. Alright students, what is the significance of temperature T degrees Celsius? So what is this? This is solid, this is liquid, this is gas. So B to C, this is of course melting. So T degrees Celsius is giving you the melting point. Okay, so what is the significance of it? It is the melting point of the solid. What next? What is happening to the substance between C and D? Okay, C and D, what is happening? So we will write in liquid state. In liquid state, the temperature is rising. The temperature is rising. Isn't it? From C to D, the temperature is rising. Okay. Why does the temperature does not change between B and C? So we will write that state change happens, right, and thermal energy is used in increasing potential energy of between the particles. Okay, but the kinetic energy, the average kinetic energy does not increase, right students? So that is about the state change. Okay, so between B and C, the state change happens from solid to liquid, but there is no temperature change because the kinetic energy does not change during this time, and it's only the potential energy that is changing. Copy this down if you want to, and then we move forward. Alright, an electric kettle is rated at 25 watt. Calculate the quantity of thermal energy generated in 2 seconds. So, we will write power times time, and it's going to be 25 times 2. So, that's going to be 50 watt. Rise in temperature of 150 gram of water in electric kettle if the electric kettle is switched on for 5 minutes and the specific heat capacity of water is 4000 approximately. Alright students, so let's do this. So first let's calculate how much is the energy supplied. So it is 25 switched on for 5 minutes. So 5 minutes is like 5 times 60 seconds. That is the energy that the kettle has supplied. Okay, so let's calculate this first. 25 times 5, 25 times 5 times 60. So that's giving me 7500. Alright, so this is 7500 joules. And now let's equate this to mc delta T. Now 7500, m is going to be 0.15 students. I hope you are aware. Look at the unit here. It's joule per kg per Kelvin. So you have to take the mass in kg. Okay. What about the specific heat? So it is 4000, and from here you can calculate the value of delta T. That is what we have to find out. So let's divide 7500 divided by 4000 and then divided by 0.15. So that is giving me 12.5. That is giving me 12.5 degrees Celsius or 12.5 Kelvin. Students, it does not make a difference. Keep that in mind because we are talking about delta T. That is why the unit here is Kelvin per Kelvin. It does not matter even if it was per degree Celsius. Copy this down, then we move forward. All right. Next, some solid wax at room temperature was heated until it melted. Then its temperature was taken every minute as it cooled down back to the room temperature. Figure shows a graph of the results. Explain what is happening to the wax during A to B. So A to B, it is obviously fall in temperature, right students? Fall in temperature. B to C, so this is solid students. This is going to be liquid, and then it is going to be a gaseous state if like further. Okay, so now B to C. So B to C, we will say what is happening. It is melting that is happening. C to D, again fall in temperature or drop in temperature. I hope you should be able to do it, students. Reduce the melting point of wax from this result. Of course, the melting point is going to be 60 degrees Celsius. Easy students, I think you should be able to manage this much. All right, let's move forward then. All right students, so the last question for today. A cooking pot contains 0.80 kilogram of water at 40 degrees Celsius. So we can see a cooking pot and 40 degrees Celsius, the water is at 40 degrees Celsius. How much energy must be supplied to boil all the water? So we have to boil all the water so that the pot is dry. Okay, fine. The specific latent heat of vaporization of water is 2.26 into 10 raised to the power 6 joules per kilogram. The specific heat capacity of water is 4200 joule per kg per degree Celsius as we know. Assume that the pot does not take any heat. So this thing is important. The pot does not take any heat. Alright students, so let's do it. So first we have to take the water up to the boiling point. So let's do that first. So let's take water from 40 degrees Celsius to 100 degrees Celsius. For that we will use the formula mc delta T, isn't it students? So the m is, the value of mass is 0.8, the specific heat capacity of water is 4200. I hope you are able to do it. Solve it yourself first, then go for the solution, and delta T is going to be 100 minus 40. Why students? Because we need to take it up to 100 degree. That is what the boiling point of water is. Let's do this calculation very quickly then. 0.8 times 4200 times 60. Alright, so this is giving me 201 201,600. Let's keep it like that for now. Okay, 201,600, that is 2,16,000 joule. All right, students. Next, let's do one thing. Now, water is at 100 degrees Celsius. So let's convert that to steam at 100 degrees Celsius. So now it is the step of state change. So we are not interested in further raising the temperature. We are only interested in taking it in the form of steam. So delta Q, now the formula that we are going to use is M into L, students. Again, M is 0.8 and the latent heat of vaporization is going to be 2.26 into 10 raised to the power 6. So let's do this calculation. 0.8 times 2.26 times 10 raised to the power 6. All right, students. So what I am getting is quite a lot. This step will take a lot of heat, and this is 108. Okay, students. 180. All right, 8000 joule. So now let's convert them in the standard form, students. So this is 2.016 into 10 raised to the power 5 joule. Okay, you can do this calculation yourself though, and this is going to be 1.808 times 6. Right, students. So let's add this. So 18.08 plus 2.016. So what I am getting is the total heat that is going to be first step Q1 and then second step Q2. So that is giving me 20.096 into 10 raised to the power 5 joule, students. All right. I hope you can cross check the calculation though. So it is approximately, if we round it off to two significant digits, so this is going to be 2.0 into 10 raised to the power 6 joule. Right, students? I hope you understand this much, and this should be easy for you. So this is the amount of heat that you need, that is 2 million joule, students. So you need 2 million joule just for 800 gram of water to boil the water from 40 degrees Celsius. Right, so now you understand that there are two things that can happen when you supply thermal energy. One is temperature change and the next one is the state change. Right, students. So this was part 2 of thermal physics. Very soon we'll come up with part 3 where we are going to study more aspects of thermal physics. But this was in continuation with the first one. So now you understand everything, I hope. What are the three states of matter? How do we interconvert between these states? And how do gases behave? Like what was Charles' law, what was Boyle's law, what was Gay-Lussac's law? So all these things I hope you are able to understand. Right, students? So if you are liking our work, please give it a thumbs up, like our channel, subscribe to our channel, and that really keeps us motivated to do further work. Also, in the comments, you can let us know what other videos you want us to come up with. We will be more than happy to help you in the right time. Right, students? Thank you so much for your time. I will see you very soon. Thank you so much. Bye-bye.
If you enjoyed this video, please don't forget to like, share and subscribe to our channel.